All right, so let's go to here. We've already talked about alkenes and alkynes. We're going to actually start here with making them, right? It's not that, let me put the date on here. All right, so we're going to start here. And in order to make alkynes, is basically a double elimination, right? So you can see right here, right, if I start with a alkyl dihalide and I treat it with 2 moles of potassium hydroxide, that'll actually give me an alkyne. And again, if you remember back from when we first started talking about functional groups, right? An alkyne is just a carbon-containing compound that has a triple bond in it, right? And this is this elimination is a E2, if you recall that from the previous section, right? It's just 2 of them happening, and that's what this down here is showing, right? You add 1 equivalent of KOH, and then you pull off HBr. Let me just show you that. All right, so you lose HBr there, and then you add a second equivalent of KOH, and show you that. That's going to come in, pull off another proton. Sorry about that. Like so, right? So it's a 2 E2 eliminations. Let me put that OH up here too. Right. So with the synthesis of alkynes, it's fairly simple. It's just again 2 moles of base and 1 mole of alkyl dihalide. Right. And then over here, as far as the naming is concerned, I don't want to get too deep in the weeds on nomenclature because you know that we're going to do a whole section on that coming up after this. But for something, for an alkyne, there's no cis or trans because all triple bonds are linear, right? So it can't be cis or trans, right? But then the functional group, the alkyne functional group starts here, right? And let me make this kind of clear too, because I know it's a common mistake for alkynes, right? These are both carbons. Right? I know it's drawn out in skeletal form and you can't really see the carbons, but there's a carbon at each end of that alkyne. So you'll start numbering from here. 1, 2, 3, 4, 5, 6 carbons. So this will be 1 hex for 6 ion, right? So the 1 tells me where the alkyne is, and the ion is my suffix. Just like for alkenes, the suffix was -ene. All right, and it asks you down here to draw 2-methyl 3-octane. What do you think? What's the 2-methyl 3-octane? How many carbons are in the longest chain in there?
8.
8. Good. So I'm going to say, and it's going to be at carbon 3. So 2-methyl 1, 2, 5, 6, 7, 8. Right, so you can see there we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. At carbon 2, right, we have a methyl group as a substituent, and then the alkyne is between carbons 3 and 4. That rule stays the same as it was for alkenes, in that you give the alkyne the lowest number possible. So the 3 tells you the location of the alkyne, the 2 tells you the location of the methyl group, and then the suffix "-ine" tells you that it's a triple bond, and the oct tells you that it's 8 carbons. All right, any questions about that part? All right, let's go to the back part of this handout, and we're going to talk about a bunch of different reactions of alkynes. All right, we're going to talk about let me put the data in first. We're going to talk about hydroboration. What you're going to find out is that a lot of these reactions are very similar to alkenes. All right, we're going to talk about Mercury catalyzed hydration. Right, again, when we talk about hydroboration and then mercury catalyzed hydration, both of these reactions are similar to what we did with oxymercuration and hydroboration, adding basically H and OH across the triple bond instead of a double bond in this case. We're also going to talk about alkyne reduction. And the last thing we're going to talk about is alkynes as nucleophiles or bases. Right, and then that's all dependent on the type of substrate you react to alkyne with. So that's what we're going to cover this week. Right, so we're going to jump right in and talk about this hydroboration. And one of the things about the hydroboration oxidation, right, it follows the same paradigm, right, as the alkene. When we did alkenes, what was the regiochemistry for hydroboration?
Anti-Markovnikov.
It's anti-Markovnikov. Here, it's still going to be anti. Right? It's still anti-Markovnikov. Right? Still anti-Markovnikov. Nothing changes there. The problem with alkynes is that when you add, once you do the oxidation step, you get a compound like this that's called an enol. Right? And so the enol itself is unstable. And so that converts to what we call the keto form through a rearrangement. right? It converts through a rearrangement, and there's a specific name for this rearrangement. It's called tautomerization or tautomerism, right? So I'm gonna show you. I'm gonna add a page in so we can talk about that, how that happens. All right. So let me add a page here. Where am I? Here. All right. So let's talk about that. It's called keto, enol, tautomerism, and all of your alkynes, when if you convert them to, if you do hydroboration or mercury catalyzed hydration, either one, you're going to get an enol. So let's say we start with this triple bond, and then I'm going to add.
Dr. Russell,
Yes.
what were you trying to say on the top? Where's that T word? I can't really make it out.
Tautomerism. Let me rewrite it a little with a little bit better penmanship. Right, it's tautomerism. I'll explain what that means in a second. Sometimes my brain is moving faster than my hand. All right. So if I take this alkyne and I react it under hydroboration conditions, I'm going to get this, which is what we call the enol. All right. Now the ene is for the alkene. The all, let me change that color right quick. It's for the alcohol, the OH group. Right, so you can see the ene part right here, and you can see the all part right there. Right, but the enol itself is unstable. Right, but is everybody okay with that product? Because what I did was the exact same thing I did with the alkene. The only difference is here there are 2 pi bonds instead of 1, and so I used up one of those pi bonds, and the other one stayed intact. Are we okay with that? Because the outcome is still the same. I'm still getting the alcohol, and it's still anti-markovnikov. All right. So let me show you what happens within this tautomerism.
Wait, Dr. Russell.
Yes.
Why is it unstable?
I'm getting ready to show you. So the enol will much rather be it will much rather be in the keto form or the carbonyl form. So let me show you what happens. Then I can explain why. All right. So we go from here. Let's see if I can copy that so I don't have to redraw it. It's okay to cheat every now and then. When you write notes now, not on the exam. All right. I'm going to put this hydrogen over here to make this a little bit more, easier to see. So this tautomerism is actually a type of rearrangement. And if you remember the 4 types of reactions, we said addition, elimination, substitution, and rearrangement. So rearrangement is like an intramolecular movement of atoms or electrons, right? So what happens in this case, let me show you what happens. And I'm going to add a step in, even though it doesn't really, even though it's concerted, I'm going to show you an intermediate so you can better understand what's going on. All right. So let's do this. Let's take the electrons here and move them here. That's going to put a pi bond between carbon and oxygen. And the oxygen looks like a navel orange. All right. And then by the same token, I'm going to force these electrons here onto this carbon. It's kind of like a resonance form. So the tautomer, well, the precursor to it, let me draw it right here. Yes or no? So oxygen is positive now, and carbon is negative. Anybody not see that? So I use the oxygen, the lone pairs on oxygen to make a carbon-oxygen pi bond. And then I broke the carbon-carbon pi bond. And now that's a lone pair on carbon. So now it's like from here, it's just a simple proton transfer. And that's going to give me this. And this is the
Are you drawing right now?
yeah, is it not showing up?
I think it froze, or maybe.
Hold up, let me reshare. My computer's been being stupid all morning. I guess it's Monday for everybody, including the computer. It's coming up, I think. All right, can you see it now?
Yes.
Right, so this is again, the Enol. Right, and then the other form is the keto form, the carbonyl form, right? So the two species, we call them tautomers of one another. They're just, that's the term we use for the rearranged enol form. So I think that was you, Brittany, that asked why is the enol not stable? It's stable to a point, but if you look at the keto form, what I did was, you calculate the delta H, I broke a carbon-carbon double bond and I made a carbon-oxygen double bond. So that's a stronger bond. So that's why this rearrangement happens, because you're able to break a weaker bond and make a stronger bond. All right. So anytime you do hydroboration or mercury catalyzed hydration on an alkyne, it's going to go through this rearrangement. It's not going to stay in the enol form, right? Let's go back up to the other problem here. Right? Can you see right here for the mercury catalyzed addition of H2O? Right? It's not oxymercuration, but it's still a similar reagents, right? You got a triple bond and you treat it with mercury sulfate, sulfuric acid, and water. And what you'll notice is it follows the same regiochemistry. It's still Markovnikov. Right, so it's still Markovnikov, but it doesn't stay in the enol form. Again, it's going to rearrange to the keto form. So when you see these reactions, and the question is predict the products, right? You're gonna either either a ketone or aldehyde is always gonna be your product. It's not gonna ever be the enol. The enol is the intermediate. But equilibrium, you can see the little equilibrium arrows here. Excuse me. The equilibrium is always gonna favor the keto form. All right, questions about that? No question. All right. So that's the hydroboration and then mercury catalyzed hydration. You get again the enol, which rearranges to a carbonyl in both cases. We're going to look at some examples too, because I have another handout that we're going to work from. But this is just for just to get our our palate wet with these reactions. And then if you look at letter C, all right, if you look at letter C, right, it's an oxidation reaction, right? And the oxidant is it's kind of similar to ozonolysis, but it's a different set of reagents. It's potassium permanganate. It's like it's frozen again. Come on, man. Sorry about that. All right. So with the oxidation, this reaction is the same if you think about ozonolysis, right? It's the same concept where you take the alkyne and crack it in half, right? And each carbon in that alkyne becomes a instead of a aldehyde or a ketone, each carbon becomes a carboxylic acid. Can y'all see that? Anybody not see that? And I'll say this, as far as these reactions are concerned, if you are sketchy on your functional groups, then it makes this a lot harder. So my suggestion is, if you're sketchy on your functional groups, you need to go back and review them, because if you don't know what a carboxylic acid is, then it's going to make knowing the product of this reaction very difficult, right? But this is just like ozanolysis, in that you take the triple bond, you crack it in half, and both carbons in that triple bond become carboxylic acids. All right. All right. Any questions about that reaction? If you notice, we're not going through the mechanism because we talked about so many different mechanisms with the alkenes. These reactions are almost mirror images of the alkene reactions. It's just slightly different products. All right. Let's go to D. Right. So this is an example of reduction. All right. What was the definition of reduction I gave you the other day? Anybody remember? I know it's Monday, but man.
Is it less bonds to oxygen and more to
Or
hydrogen?
more bonds to hydrogen, right? So with the with the alkynes, you can reduce it all the way down to a alkane, right? By basically killing both pi bonds. If you just use the same set of reagents, hydrogen and then palladium on carbon, that'll take an alkyne down to an alkane. It'll take an alkene down to an alkane. There's no specificity or selectivity. But with alkynes, you can also make them either cis or trans, right? If you want to make a cis alkene, let me not say that. You can take an alkyne and convert it into either a cis alkene or a trans alkene. All right. If you want to make it into a cis alkene, cis meaning, again, this is stuff that you should remember from before. Cis meaning that both groups are on the same side. If you want to do that, there's a specific catalyst that you use, a specific type of reagent. It's called Lindlar's catalyst. Uh-oh. So when you see Lindlar's catalyst in the presence of an alkyne and hydrogen gas, that's a giveaway that the alkyne is going to get converted into an alkene, but it's going to be done in a cis fashion. So your alkene in the product is cis. And then if you want to make the trans alkene, just change the reagents. It's lithium and ammonia, right? To make the trans. So if you take the alkyne and react it in the presence of lithium and ammonia, you're going to get the trans alkene. And so I have a mnemonic up here to help you remember that, right? LCAT, little children always tripping, is Lindlar's cis and ammonia trans, LCAT. If you get that mnemonic down, then when you see the reagents, you'll be able to determine or distinguish between the two reactions, because one of them is going to give you a cis alkene, the other one is going to give you a trans alkene. Right? So Lin-Lars is cis, ammonia is trans. All right, questions? Any questions? Everybody's quiet and muted. All right, so again, reduction of an alkyne, you can reduce it either to a alkene, or you can reduce it to an alkane. And then again, you can do the alkene reduction or the alkyne reduction to alkene with selectivity. You can make it a cis alkene or a trans alkene. You might not think that's important, and on the surface it doesn't look important, but if you're building a larger molecule, then you need reactions that are selective like that, where you might, within the context of building the larger molecule, you might need a cis alkene instead of a trans alkene. All right. All right. Let's go to another section here, and this is using alkynes as nucleophile. It can be a nucleophile or it can be a base, right? So the alkyne can be used. Frozen again. Come on, come on, come on. You about to get replaced. All right. So the alkyne, the pKa of that protons is about 25, right? So if you react that in the presence of a base, like sodium amide or butyllithium or potassium terpbutoxide, let me show you what that looks like. So butyllithium is, it's a 4-carbon chain, and carbon, that fourth carbon actually has a covalent bond to lithium. It's a really, really, really strong base, right? And then potassium terpbutoxide, which is here, is a alkoxide base, where it's negatively charged oxygen and a positively charged potassium. Very strong base. And so any one of these bases is strong enough to pull off this proton, which has a pKa of 25. Right? And when you pull off that proton, you generate what's called the acetylide anion. Now, this can be a nucleophile, or it can be a base. It just depends on what context you use it in. Right? It can be a nucleophile or it can be a base. It just depends on how you use it. All right. If you react that with a primary electrophile, like a primary alkyl halide, it's going to act as a nucleophile. If you react it with a secondary or tertiary, it's going to be a base. So let's see what happens. All right. So here's the acetylide anion. I have a methyl bromide, which is a methyl substrate, right? Yeah, I can also use a primary substrate. They're gonna react the same way. But here, what happens in this case is I get substitution. because the carbon is in this case it's a methyl carbon, but it could also happen on a primary carbon. So I get SN2 type substitution on those types of carbons. If I make that carbon more substituted, so if it's a primary carbon or a methyl carbon, it's going to be a nucleophile. The acetylide anion is going to be a nucleophile. Right? If I react it with a secondary carbon, then it's going to be a base and do elimination, E2 type elimination. Right? So you'll have this is going to come here. And it's just going to eliminate in an E2 fashion. Right? You can see in the product of any elimination is a alkene, right? So the triple bond can be a nucleophile or it can be a base, depending on what you reacted with. You react it with a primary or methyl alkyl halide, it acts as a nucleophile. If you react it on a secondary or tertiary alkyl halide, then it's going to be a base and do elimination. All right. Questions about that? I have a mnemonic for that too, right? Over here, there's a mnemonic. So 1S, 2, 3E, 1 sausage, 2 or 3 eggs. 1 primary, one is for primary. So primary is substitution. Secondary or tertiary is elimination, right? And so if you have a primary alkyl halide in the presence of the acetylide anion, you're going to get substitution. You have a secondary or tertiary alkyl halide in the presence of that acetylide anion, you're going to get elimination. So that's a good way to remember that. All right, 1S, 2, 3E, 1 sausage, 2 or 3 eggs. A good way to commit that to memory. All right. Any questions about anything we talked about? I'm sorry for that delay with my screen. All right. Let's go to a so let's go to a quick reaction right here. So it says, draw the result of the arrow pushing mechanism shown below. Again, even if you don't know a mechanism, you should be able to follow arrows logically and give a conclusion based on what you see. So based on that middle structure right here, what should go here? And let me help you real quick with that. The ring doesn't change because the ring ain't doing nothing. It's there, but it's not reactive. And what's the name of that structure, the second structure? It's called an enol, right? So what, based on the arrows that are shown, what should that structure look like, the intermediate? What is it going to look like? You can chime in anytime. I mean, I'll keep writing.
Oh well, yeah. Carbon and oxygen is gonna form a double bond.
Oh, okay. Gee, thanks. You're right. I'm just messing. So you have a double bond here. Is that right?
Yes.
And it's going to be protonated. And it's positive, by the way. Oxygen is. All right, now we need to put the arrows in to go from this structure to the keto form. How do we do that?
Will you take the red carbon and connect that to the hydrogen that's with oxygen, and then break that bond between hydrogen and oxygen?
Yeah. But you're actually connecting the hydrogen to the red carbon, right? It's the other way around.
Oh yeah.
But you're right, though. Sorry about that. So yeah, so you'd attack do a proton transfer, right, to that carbon that's labeled in red. All right, and that'll get me to the keto form of that. All right, let's go to the next one. You got the enol and the intermediate. What would you do to get to the final product? Look at the difference in where the enol is too. Right here we did mercury sulfate and then water and sulfuric acid. So what is that? What is the final form of that going to look like?
Is the blue carbon gonna have a hydrogen, and then the green oxygen is just gonna be neutral?
So you're going to pick up this proton right here. Is that what you're saying?
Yes.
And then break the OH bond like that.
Yes.
Yeah, I'm not going to color code these, but you're right. Maybe I should color code them. Any questions about that? I know it's the first time you've seen it, so it's gonna take some practice. Let me put the date up here.
I actually have a question.
Come on.
When are you gonna upload this assignment?
This sheet is I think it's already open. But the module's not open.
Okay.
Yeah, let me open the module right now. So dang, it's the 4th module. Come on. Yeah, let me make it available now. And all of my working ahead last week trying to get ready for the exams and all this other stuff, I forgot to open it. But it's open now, and that is under assignments.
Thank you.
Mm-hmm. And you make sure the pre-assessment and all that stuff is in there. I think it is. Yep. I did send videos for Alkynes, yes?
I didn't get any videos.
All right. I don't believe you. I'm just joking. I'm just joking. I'll send them today. I thought I sent them last week, but I may have been mistaken. But I will. I'll send it today. All right. Any other questions? We're gonna come back to this Wednesday, so you need to be looking over this section. There is. Let me see. In there, it's the 4th module, and the videos are in there. But I'm gonna send you the links anyway. And then under, I think it's supplementary resources. Yeah, there's an Alkynes overview. It's a link to this is a link to another website, and there is pre-assessment, post-assessment. There's gonna be obviously, once you watch the videos, there's a quiz associated with that. Let me see. Yeah, everything is the same. And then that handout that we were just working on is in assignments. And then the other handout, the overview, you should have already had that, but I think I put it in here too. Let me double check. Let me double check.
The overview is in Module 3A reading assignments.
Yeah, I think I put it in here also. Yeah, it's right here. So Alkyne, it's the same one from 3A, but it's abbreviated to only include the alkynes and not the alkenes, if I'm not mistaken. Let me double check. There's a PowerPoint in there too, but I'm really looking for this document. Be looking under readings. I think I put that in here too. Come on. Yeah, it's here too, but it's under readings, but it's only the alkynes. Yeah, so it's just the reactions that we just did. All right. So yeah, all the information is there. But I am going to upload these notes from today, and we're just going to keep rolling. All right. Anybody have any questions for me?
I had a question.
Go ahead.
So I know you usually take down the modules after like every exam, but could we have an extra day for
Yeah.
module 3A?
Yeah, sure.
Okay. Thank you.
Yeah, you're welcome. I didn't realize this PowerPoint was in there. All right. I'm going to stop the recording and stop the meeting and let y'all go because it's 12 o'clock. And I'm going to send these, I'll send these, the notes. I'll upload the Blackboard, and then the video, I'll upload to YouTube momentarily.